Continuing our review, let's recap how we write atomic symbols and then just look at the periodic table and remember a little bit about its structure and how everything falls the way it does. All right, so we know that we have our atomic symbols where we've got our mass number, our atomic number, our chemical symbol. Occasionally you might see the chemical symbol or name and then a dash and then the mass number. So if I have a given element, what never changes about that element? Think about that for a second. When we have our protons or neutrons and our electrons, what never ever changes? The protons. We're always going to have the same number of protons. If I change the number of protons, I change the identity of the element. Our atoms can ionize, gain and lose electrons. We can have different isotopes, and our isotopes differ in the number of neutrons, not the number of protons. So again, I change the protons, I change the element, okay? And so atomic number is just the number of protons, and then mass number is protons plus neutrons. So if we look at carbon, okay, so carbon, we've got, our carbon 12 here, so that's our mass number. So if I have a carbon 12, how many neutrons do I have? Okay, well, I can take that mass number minus the number of protons, and I get 6 neutrons. Okay, I can also do it this way, or I can do something like this, because again, we're always going to have the same number of protons. But if I'm asking for an atomic symbol, that's what I'm looking for, is the full shebang there with the mass number and those protons there. Okay, so carbon has 3 main isotopes, carbon 12, carbon 13, and carbon 14. So carbon 12, carbon 13, and carbon 14. And so the only thing that's changed there is the number of neutrons. So in carbon 12, I have, here I can do this. I can do protons, neutrons, and electrons. Okay, none of these are charged, so these are all neutral species. So all of these are going to have 6 protons. And if they're all neutral species, if protons are a +1 and electrons are a -1, how many electrons do I need to have a neutral species? Well, I would need 6 for each of those. Okay, but my neutrons, I'm going to have 6 here, 7 here, and 8 there. Okay, and so again, hopefully you did that a bunch of times in your previous course. Now, when we think about neutrons, these are kind of like nuclear glue. They hold everything together, all right? They're there to buffer all of that positive charge. So one thing that if you go on to the next semester of chemistry, in your nuclear chemistry chapter, you'll learn is something called the band of nuclear stability. So there's actually a way we can basically predict how many neutrons that we need per proton during basic or various regions of the periodic table. So like elements 1 to 20, they need a 1-to-1 ratio for stability. Okay, when we get outside of that, that's when we start to see instability. So if we know about carbon 14 is our radioactive isotope of carbon. Well, carbon 14 definitely has a greater than 1-to-1 ratio of our neutrons to our protons. We have 8 neutrons and only 6 protons. So there's some instability there. It's like elements 20 to 40 is about 1 to 1.25 ratio. So I need more neutrons now to buffer off all those protons that we're putting together. And then when I get above element 40, now we're looking at that 1 protons every 1.5 neutrons. And again, once we get outside of those ratios, then we start to see decay. And we can actually predict the mode of decay based on the ratio of the protons to neutrons. It's really interesting the way it all works to try to hit stability. Okay, and so we have our periodic table here. I just find this interesting when we think about when everything was discovered. So the light blue is everything that was discovered before 1800. So we knew a lot of stuff before then. And then as time went on, we started discovering more. There wasn't a whole lot discovered in that 1900 to 1949 region. And then the 1950 to 1999, so we've done a little bit more since then. You know, this whole region in here, we've started filling in. Okay, but that whole 1915 to 1999 section, most of those aren't so much discoveries as things that we have created in particle accelerators. We smashed them together, and they've existed just long enough for us to go, cool, new element, but they're very unstable. And what's really interesting is if you look at newer periodic tables and you see how this has been filled in more, is the even numbered elements, the ones with even number of protons, we've managed to get those to be stable before the ones with odd numbers of protons. So that's just a kind of interesting thing in how we're starting to understand the structure of the atom. They're starting to see with the nucleus, so just like we have things like the spin pairing with the electrons and everything, that they're starting to see evidence of like pairing up with protons, which totally goes into this thing where we're seeing even numbered elements stay stable long enough for discovery before odd number elements. So it's very curious. When we think about the elements, you know, we can look at on Earth, what's the most abundant. So oxygen's a very abundant element, 46.4% of the elements on Earth, oxygen. And so some we have present in great amounts. The rest of them we have present in what we call trace amounts. So not a whole lot of them around. Once they're gone, they're gone. So, okay. We can look at the abundance in the human body, see what we have a lot of. Stands to reason that there's a heck of a lot of hydrogen and oxygen in the body, because what are we most of, or mostly made out of? Water, right? And then lots of carbon, because we're a carbon-based life form. When we look at the elements and we start to put them together, we see these repeating patterns. Okay. We can start lining up the elements based on those repeating patterns. And then we can start to put together the periodic table. Now, before we got to today's periodic table, there was a periodic table that looked like this. It was called the Table of Periodic Law. This was published by a German chemist named Mendeleev. And so he first put this together. And it's really interesting because if you think about it, we have all sorts of modern instrumentation that will allow us to learn all sorts of things about what we're studying. What Mendeleev had was classic wet chemistry. That's it, classic wet chemistry. And so, you know, he was able to, you know, figure a lot of this stuff out just with that classic wet chemistry. Now, he was German. This was a long time ago. So, you know, we're used to things like water. We would write H2O. Okay. If you look here, I have superscripts instead. So he did things with a superscript instead of a subscript like we do. All right. Now there's a lot of things that are on here that we do have today. There's a few things like, you know, there's no element J. All right. And that's on here. So that was kind of a placeholder. These two right here, he put placeholders in. And these are real elements that, based on the properties of the elements around them, he was able to predict the properties of. So 2 elements there. Think about that. Hopefully you learn about these in 120. If you remember what these 2 elements are that he was able to predict the products of accurately from his periodic table, drop them down in your notes, because I'm curious if anybody remembers. Okay. All right, and so here we have this. And so you can see what I was saying, you know, there's this, those are even numbers. Now, this table is dated 2005. You can actually start to see some of how old of a periodic table is because of what's filled in and what's not. These have these placeholders. Then they were assigned these UU designations. And then finally, when they were able to be confirmed by multiple particle accelerator labs, then they were given an official name. Now, have we found all the elements yet? So there's a couple of supplemental videos that I have that I've posted that are put on by things like the American Chemical Society to go along with this so that you can see some more of that background. And in fact, one of my latest issues, do I have it? No, it's not on my desk right now. But one of the latest issues of Chemical and Engineering News actually is talking about filling in these. Oh, here we go. I remembered where I put it. So here, one of my latest issues, Japan takes the lead in elements 119 and 120. All right, so here's 116, 117, 118. That would end off period 7. Well, elements 119 and 120 would start period 8. So this is big stuff. We're still working on these things today. So it's very cool. All right. When we look at the elements, we can start to see different properties. So we know the regions of the periodic table. We have our metals, we have our nonmetals, we have our semi-metals or our metalloids. Most of the elements on the periodic table are metals. We know there's different periodic trends on the periodic table. I really like our halogens because our halogens show the trend in metallic behavior really well because we know we get more metallic as we go down the periodic table. And our halogens, they start off as a gas, all right? Then we have a liquid and then we have a solid. And so obviously the solid is going to be more metallic than the gas. Even though they're all nonmetals, we get more metallic in behavior as we go down. Okay, in our different groups, our vertical columns there, like group 1A, we see similar behavior. We see trends, similar reactivity. Does anybody remember why? Think about this for a second. If you remembered, it's due to valence electrons. You're correct. So this is our group 1A. Okay, they have 1 valence electron. And so we know that most of the chemistry with these main group elements especially is happening with those valence electrons. And so if each one of these has 1 valence electron, then we're going to see similar behavior. Okay, our alkaline earth metals, this is our group 2A. Okay, and then what do those have in common? Oh yeah, 2 valence electrons. Okay, so we see similar behavior, similar reactivity there. Okay. All right, and then again, we go to those halogens, and so we definitely see that trend in metallic behavior as we go down. This is group 7A, 7. And then we get to our noble gases, and what is important about our noble gases? Well, they have full valence shells. This is group 8A. Their valence shells are full. And they're relatively unreactive. They don't like to do much because they're already, hanging out there with a full valence shell. So they don't need to react to do a whole lot. Okay, we can force them into doing things, but they don't really like doing anything. They're happy the way they are. In fact, when I was in high school, back in the 90s, when we were learning about valence electrons and everything, we were taught that an element was either happy or it was sad. And so elements like to react to get their full valence shell, to get a full valence shell of 8. And so when they react and they have their full valence shell, they're happy. And before that, they're sad. And so we were taught that the noble gases are always happy. The weird things that stick in your head. But anyway, noble gases are happy. They don't want to react. They are perfectly happy the way they are.